Hello, everyone. We are back at 621. Now we're switching topics into the next part of this chapter, where this part of the chapter is on something called implicit differentiation. And in this video, I'm going to explore it to you and see how helpful it is in a variety of problems. So let's say, for example, we have a circle that's given by the equation x minus 1 squared plus y minus 2 squared equals 16. Okay, so if you recall, that means that you're going to have a center at 1, 2 with a radius of 4. So if I was to make a circle here, we have 1, 2, a radius of 4. It's going to be up here. 1, 2, 3, 4. 1, 2, 3, 4. So if I sketch this, it will look something like that. Okay, so there's my circle. And what if I said find the slope of the line tangent at x equals, we'll pick an arbitrary number, 3. At x equals 3. So I want to find the slope of the curve at this point here, and the slope of the, I say curve, but slope of the tangent line, which the tangent line is the slope of the curve at that point. So I want to find the slope at those 2 points. Now, how do we do it? Well, in order to find the derivative, we'd have to get this in terms of y. So if I do that up here, I would have y minus 2 squared is equal to 16 minus x minus 1 squared. And then I would eventually get to the point where y is going to equal the square root of 16 minus x minus 1 squared plus 2. And we know how to take derivatives now, so we want to find the derivative of this function. Well, that's going to be, now I can rewrite this as 16 minus x minus 1 squared to the 1/2, because it's a root. Remember, it means power over root. So that means with derivatives, with the power rule, I bring that in front. So it'd be 1/2, leaving the inside alone from the chain rule to the negative 1/2, times the derivative of the inside, which the derivative of 16 is 0, and the derivative of this is going to become negative 2 x minus 1. And then you would do derivative of the inside again, but the derivative of x minus 1 is just 1, so we don't have to account for that. And then the derivative of 2 is 0, so we don't have to account for that. So if we clean this up a little bit, we would have that the derivative is going to equal, or the negative 2 and the 1/2 will go away. So we're going to get negative x minus 1 over the square root of 16 minus x minus 1 squared. Okay. And then from there, we have our derivative function. And notice we wanted to find the derivative at 3 was our problem. So then we did dy dx at x equals 3. We will find both those, and just remember we have to do the plus and negative of that square root there. So then we'll have negative 3 minus 1 over plus or minus the square root of 16 minus 3 minus 1 squared. Simplifying that, I'll have negative 2 over plus or minus the square root of 16 minus, that's going to be 2. 2 squared is 4. 16 minus 4 is 12. And I can break 12 down as 4 times 3, which will allow me to take out the 4 as a square root and write that as 2 root 3 plus or minus. A simple final step is I would say that it's negative 1 over plus or minus root 3. So what I can see from this picture, because of our picture here, I can say that at x equals 3, you have a slope, dy dx is going to equal negative 1 over root 3. And that looks like that's happening at this one, where the slope here, if I use m, equal negative 1 over root 3. Well, don't use m. You guys know derivatives. Sorry, thinking my IM1 class. of the slope here, d dx, dy dx, will be negative 1 over root 3, and the slope here will be positive 1 over root 3. Okay. And that is great. Now, but there has to be an easier way, because that was, not that it might have been necessarily hard, but it's strenuous. For example, y, if I write this in red, do we have to get y by itself first in order to differentiate? And the idea of that is, no, you don't. And this is where implicit differentiation comes into play. So keeping with the same problem, I'm going to do it right here, and I'm going to do it all in red now. So this is now implicit differentiation. Okay. So the circle was x minus 1 squared plus y minus 2 squared equals 16. Okay. Now, implicit differentiation means you just take the derivative of the entire function. So we're going to do d dx of this entire function. No need to get y by itself at first. Okay. So if we do the derivative here, let's see, the derivative, and we're taking the derivative with respect to x. How is this changing as x changes infinitesimally small? So the derivative of x minus 1 squared would be 2 times x minus 1 to the first times the derivative of the inside, and the derivative of x minus 1, well, the derivative of x is 1, and minus 1 would be 0. Okay, good. Plus, now, how do we do the derivative with respect to y? This is where it gets a little bit interesting. So before we even get there, we can apply the chain rule where it's the derivative of the outside, leaving the inside alone, by power rule, times, now what's the derivative of y minus 2? So maybe as a side note, I'll bring this up here. What's d dx of y minus 2? Okay, and that's interesting, right? Well, the derivative of y with respect to x, all we know is that y is a function of x. So maybe we could write this as d dx of y of x minus 2, in which the derivative of y of x, we know that it's going to be a function, but in terms of x, but we don't really know what that is. We just know that the term x is involved. So what we do is we just leave it as dy dx. The derivative of y minus 2, so the derivative of y is just going to give us dy dx. It's the derivative of that function with respect to x, minus the derivative of 2, which is 0. So then we just get dy dx. So we get times dy dx. So that's the derivative of y minus 2 equals, and the derivative of 16 is 0. And now all we have to do is just get dy dx by itself. So if we do that, we would get dy dx. I'm going to minus that side over. So hold on. So we have 2 times y minus 2 is attached to the dy dx is equal to negative 2 times x minus 1 if I subtract that over. And then divide this to both sides, and I will have dy dx is equal to negative 2 times x minus 1 over 2 times y minus 2. And simplifying one step farther, dy dx is equal to negative x minus 1 over y minus 2. And there is the derivative of my function, of that circle function. And notice, though, that this, when we do implicit differentiation, now we have an x and a y. So this, find a slope at a point, notice the reason it has an x and y is because there's two slopes here. So that second variable y matters because that differentiates which slope we want to find. So say, for example, I keep at this, and we keep doing the same problem. Let's find the slope, the line tangent at 3, but with our implicit differentiation example. So what's dy dx at x equals 3? Well, notice in order to use this, we also need to have the y value. So if we look at our original function, which is here, we just have to get y by itself. So then we would have 3 minus 1 squared plus y minus 2 squared equals 16 that would make 4. So we'd have y minus 2 squared is equal to 12. If you subtract that 4 over to the other side, and then you'd have y minus 2 equals the square root of 12 plus 2. And then, because I would obviously add the 2 over, and I can break down square root of 12 as 2 root 3 plus 2. Good. So there's my y value. So if I was to find it x equals 3, technically, there's 2 slopes I have to find it at. The positive y value and the negative y value that goes with 3. So when I say x equals 3, it's not really x equals 3. It's actually at, find the derivative at 3, comma, 2 root 3 plus 2. And then the other one, if I have space here, which I might bring in another paper soon, find the derivative at 3, comma, 2 root 3, negative 2 root 3 plus 2 to account for the bottom point of that circle. Okay. Now, if we do the math here, as I bring in my second paper, let's see it. So the first derivative, dy dx, at that point. So x is 3, so it's going to be negative 3 minus 1 over y is 2 root 3 plus 2. Or that's a minus 2, sorry. Oh, wait, 2 root 3 plus 2 is my point, and then minus 2. Got it. And then dy dx, simplifying farther, 3 minus 1 is 2, so I'll get negative 2 over. The positive 2, negative 2 will go to 0, so I'll just get 2 root 3, which notice dy dx at the point 3, comma 2 root 3 plus 2 is equal to negative 1 over root 3, which long and behold, look here in blue, that's the same thing we had. Right? Interesting, and that's great. And that's not really interesting, that's amazing. It's us getting the same answer with a different method. And over here, if we're to check this, dy dx, at this point, we would have negative 3 minus 1 over negative 2 root 3 plus 2, and then minus 2 there, which simplifying that is going to give us negative 2 over negative 2 root 3, which tells us that the derivative at the point 3, comma negative 2 root 3 plus 2 is the point 1 root 3, which matches exactly what we're getting on the picture and with our understanding of doing this a different method. So that is implicit differentiation. And the idea of implicit differentiation is you just take the derivative of the entire function. You don't need to get y by itself first. That's not needed. But the idea is that when you get to y, you have to just write dy dx. We don't know what the derivative of y is with respect to x, so we write it dy dx, as that's what we're trying to figure out. Let me show you one more example, because I know that this was just an exploration, and I'm not quite sure at this point what the next video will look like. So a quick example here, example 3. So what if we do, and I'll use blue to separate it. Example 3, this is example 2, I guess. We have I think there was one from the homework, which I saw. Let's look at this one. So 59, let's do, and I'm writing this down, I'll show my paper in a second. And I'll even do one more to help you see this. All right, so 2 more examples using implicit differentiation. So taking the derivative of the entire thing, we would have here, and we'd have 3, and I'm going to bring the 3 out in front when I do the derivative of x, y. Well, hold on, I'm writing d dx, so let me just rewrite the problem so you know what I'm doing. Taking the derivative of the whole thing. So it's going to be 3, and then we have to do the product rule. So it's the first times the derivative of the second, and the derivative of y with respect to x, well, we don't know what that is, so that's just dy dx. Plus the second times the derivative of first, and the derivative of x with respect to x, well, that's just going to be 1. We can apply our power rule there. And the 3 is in front there, minus the derivative of x squared with respect to x, it will be 2x equals 0. And now we just solve for dy dx, so we'll get 3x dy dx plus 3y is equal to 2x, and I can just jump ahead and say dy dx is going to equal 2x minus the 3y all over 3x. And there is my derivative there of this curve up here. What about example 3? Now you could solve for y first. Sure, that works, but what if we didn't? So this can be rewritten as y to the negative 1 of x. So if we take the derivative of both sides with respect to x, we have to apply the chain rule here because it's y to a power of negative 1. So it's a derivative of the outside, so it'd be negative, leaving the inside alone, and then that becomes negative 2, times the derivative of the inside, which is the derivative of y, is dy dx. We don't know what it is equal to, and then the derivative of x with respect to x is just 1. So solving for dy dx, we would have dy dx is going to equal, well, this is the same as saying negative 1 over y squared. So if I were to multiply both sides of this equation by y squared, negative y squared, it would look something like that. So the derivative of this function is actually in terms of y only, and it's negative y squared. Good. And I hope that's right. I want to make sure. Well, let's check. What if we did it the old-fashioned way? Let's check. 1 over y equals x. If I solve for y, I'm going to get xy equals 1, and I'll get y equals 1 over x. Okay, taking the derivative of this, we'll have dy dx is going to equal, now that can be written as x to the negative 1. So then I bring that in front, and it'd be negative 1, or negative, or no, it'd be negative x to the negative 2. Sorry, I'm getting lost in all this implicit differentiation because of the power rule. Negative and subtract 1, which can be rewritten as negative 1 over x squared. Which, what's interesting about this is those derivatives are different. One's in terms of y and one's in terms of x. Now, we will talk about that farther in another day, but you can see how implicit differentiation works with ideas. You don't need to get y by itself. So I'm sorry this check might not have left you feeling that satisfaction of knowing that it matches up, but we will get there and you'll see the connection soon enough. All right, bye-bye.